Hi, this is Mrs. Basin, and today we're going to talk about the concept of equilibrium. So when we look at something called chemical equilibrium, what this means is the point at which the concentrations of all species are constant. So that means when the concentrations of the reactants and the products in a given equation stop changing. When we call it a dynamic equilibrium, we say that happens when the rates of the forward and the reverse reactions are equal. So that means you have no more net change in reactant or product concentration. The other way we represent these equations now, instead of just looking at equations with a single arrow, we're now going to represent them with a double arrow, showing that the forward reaction is occurring, but then also the reverse reaction is occurring too. If you look at the diagram here, you can see these are three different systems at equilibrium. Couple things to notice here. Notice here that equilibrium for a given system, you don't always end up with the same concentration. So these are under different conditions. You end up with different concentrations once it's reached equilibrium. The other thing to notice here is that the reactants and the products, the concentration of those is not the same. It just means that they have leveled out and that they're no longer changing. So here's a little bigger picture that shows that same thing. So you can see it's the same reaction under three different conditions, and you end up with different equilibrium concentrations. But again, they're changed. They're the same. They've leveled out, but they're not the same. When we represent equilibrium, like we said, we're going to use the double arrow. So that shows that in this particular system, you have NO2 being converted to N2O4, but then you also have some N2O4 being converted back into NO2. When we look at equilibrium, what we're looking at is how do the rates of those two reactions compare? How does the rate of NO2 going to N2O4 compare to the rate of N2O4 changing back to NO2? So to do that, we use something called the equilibrium constant. What the equilibrium constant does is it is a ratio of the rate of the forward reaction to the rate of the reverse reaction. So if you look at our diagram here, it says KEQ, that's our equilibrium constant. It's the rate constant for the forward reaction, that's our lowercase k from the last unit we did, the kinetics unit. It's the rate of the forward reaction over the rate of the reverse reaction. So what this k allows us to do is kind of visualize what's going on in equilibrium. How do those two rates compare? Do we have it, is there more product at equilibrium, or is there more reactant at equilibrium? And we'll talk about that in a little bit here. Okay, so when we write an equilibrium constant for a reaction, this is the general expression. So when you set up an equilibrium constant, you take the products over the reactants, and each product is raised to the power of the coefficient. Each reactant is raised to the power of the coefficient. And then notice here K has a little sub C instead of an EQ like it did in the previous one. All that means is it's specific for concentrations. In the next couple units, we're going to see lots of different notations next to K. Big K, it's always the same thing. It's always the equilibrium constant, but sometimes it'll specify K for certain things. So this is just K sub C, which just stands for K for concentrations. In the next unit, or in the next slide here, we're going to look at K sub P, which is specific to pressures for gases. But K, you always set it up the same way. Okay, so here's K sub P. When you set up a equilibrium constant for a gas system, it's just a little bit different notation. Notice now you're using P's. There's parentheses instead of brackets. It's still raised to the power of the coefficient. It is still products over reactants. You can also look at a relationship between Kc and Kp. So if you have a system that has gases in it, then you can compare a Kp to a Kc. Now sometimes they're the same depending on the reaction, but it is possible that they could be different. So when you use this expression, delta N is the difference in moles of gas of the product and moles of gas of the reactant. So you look at the coefficients there. R stands for the ideal gas constant because we're dealing with some gases here. So it's 0.0821 liter atmosphere per mole Kelvin. And then T is the temperature in Kelvin. So a lot of times if temperature is given in Celsius, you'll have to convert it to Kelvin. Okay, so let's try a couple example problems here. It says to write the equilibrium expression, Kc, for the following reactions. So like we said, all we're going to do is do our K equals and then we're going to take products over reactants raised to the power of the coefficient. So K for this one is going to be O2 to the third. So this is the O2 raised to the third over a concentration of O3 raised to the second. So that's all you have to do for that. Okay, if we look at the next one, same deal. K equals, brackets stand for concentration, NaCl raised to the second, because that's the coefficient, over NO raised to the second, Cl2. So again, all we're doing here is we're taking products over reactants. You're putting the concentrations into brackets to show, putting the formulas into brackets to show concentration, and then you're raising it to whatever the coefficient is. This one is going to look at the relationship between Kp and Kc. Okay, so like we said, Kp equals Kc RT delta N. So we are given Kc. So we know Kc equals 9.60. The other thing I didn't mention before is that big K does not have units. Because it's a ratio, those units are going to cancel out. So there are no units for K. So K is 9.60. R is 0.0821 liter atmosphere per mole Kelvin. And then the temperature, if we change that 300, you're going to add 273 to make it Kelvin, is going to be 573. The other thing we need to look at here is the delta N. So delta N, remember, is the change in moles. So to do that, we need a balance equation, which is not given here. So a balance equation for the synthesis of ammonia from nitrogen and hydrogen is N2, which is a gas, plus 3H2, gas. And again, we're using double arrows now, gives us 2 NH3, which is a gas. So to get our delta N value, we need the difference in moles of product and reactant. Okay, so we have 2 moles of gaseous product minus 3 plus 1, 4 moles of gaseous reactant. So that gives me a -2. This negative sign is important there, so you have to make sure if that gives you a negative value that you actually use that negative value in the equation. Okay, so now we have all those, we can go ahead and substitute those in. So Kp equals Kc, which we said was 9.60, 0.0821 times 573, and that is all raised to, okay, let's get rid of those, let's get rid of this right here. Okay, 0.0821 times 573 raised to the -2. So when we solve for all that, our Kp value is 4.34 times 10 to the -3rd. And again, K doesn't have units. All of those units, if we had left them in there, would cancel out. Okay, the other thing we can look at is equilibrium can be reached in either direction. So this particular system, it has to be, for all of these to end up in the same place, this has to be under the same conditions. So this, you can look at this from running this reaction from either direction, but the conditions were the same. The temperature was the same, pressure was the same, etc. So for this particular one, it doesn't matter if you start with N2 and H2, or if you start with NH3, you still have the same proportions of everything in equilibrium. And again, notice on the graph, once you've reached equilibrium, everything has leveled out, but the concentrations are not all the same. All right, so if we look at K, what we originally said was K kind of gives us an idea of what's going on at equilibrium. Do we have more products? Do we have more reactants? Do we have about equal of both? So if we look at the magnitude of K, look at that value, if K is a lot bigger than 1, then we know that products predominate at equilibrium. So that means that that particular reaction, what we say, lies to the right. That means there's a lot of products present. If K is a lot smaller than 1, then the reaction is reactant favored. It lies to the left. There's more reactants at equilibrium. And this would be useful because if you're running a reaction and you're trying to make products and you look at the K value and it's not a lot larger than 1, then you know you need to do something so that you can then shift that equilibrium so it does shift to the right. If you think about how K is calculated, products over reactants, those numbers make sense. If it's greater than 1, that means you've got lots of products. You've got lots of numerator. If it's less than 1, that means you've got lots of reactants, which was in the denominator. Okay, so let's look at a couple examples here. This one says you can take N2 plus O2 to make NO. That's one way of what we call fixing nitrogen. So the value for this particular equilibrium constant at 25 degrees Celsius, and again, just like before, all of these things are temperature dependent. That's why they're going to give you the temperature. So if you change the temperature, you're changing the K value. So that is 1 times 10 to the negative 30th, which is a very, very small number. So what this is asking is this feasible for fixing nitrogen? So if our desired outcome here is to make lots of NO, and we have a K value that is really, really small, that means that equilibrium is lying to the left. Okay, so that means at equilibrium for this particular temperature, for this system, we have mainly reactants because of the K value. That's what the K value is telling us. So that means that this would not be a good way to fix nitrogen. So that means we would have to change those conditions to try to shift that equilibrium so that it went to the other direction. Okay, another example. This says the equilibrium constant for this reaction, H2 plus I2 gives us 2HI, varies with temperature. So Kc is 794 at 298 K and 53 at 700 K. So at a lower temperature, you have a larger K value. At a higher temperature, you have a smaller K value. So it says, is the formation of HI favored more at the higher or lower temperature? So our desired goal here is HI. So which temperature favors the production of HI? So what we're looking for here is we're looking for the larger K value. So the larger the K value, the more products are present. So for this particular one, it's higher at a lower temperature. So the answer to this would be lower, because at the lower temperature we have a larger K value, which means that the equilibrium is, the products are more favored, it lies to the right, which means we would have more HI produced. Okay, the last thing we're going to look at in this section is manipulating equilibrium constants. So you can do things if you know the K value and you do something to the reaction, you can figure out the K value for the new reaction depending on what you did. Just like if you think back to when we used the delta H values, if you reverse the reaction, you reverse the sign of delta H. If you multiplied everything by a coefficient, you multiplied the delta H by whatever that coefficient was. K is a little bit different, so it's not the same pattern as it was for delta H. So for K, if you reverse the reaction, the K value is now the reciprocal of the original equilibrium constant. So if you notice the example here, you can see that N2O4 going to NO2, it gives you a K value of 0.212. At the same temperature, again, we're keeping everything constant, we're keeping the temperature constant. If you reverse that reaction, then the value of the K becomes 1 over 0.212. So now for K, if you reverse the reaction, you take the reciprocal of the K. So the example here is it says, write the expression first for the reaction, and then it gives us the equilibrium constant for the reverse reaction. What is the equilibrium constant for the reaction given? So our first thing would be to solve for, or to set up our K. So again, we're taking products over reactants raised to the coefficient. So N2O2 over NO raised to the second. Again, this all came from up here. And then if Kc for the reverse is 1 times 10 to the negative 30, then Kc for the reaction given would be 1 over 1 times 10 to the negative 30, which would become 1 times 10 to the third. And again, K has no units, so that would be your answer. Finally, the other way you can manipulate an equilibrium constant is you could multiply the reaction by some coefficient. So if you multiply the reaction by some coefficient, then you take the K value and you raise it to that power. So in this example here, we multiplied it. The difference between the first and the second reaction is we multiplied everything by 2. So notice the K value, 0.212, was raised to the second power. So again, little different than what we did to delta H. So a K value, if you reverse the reaction, you take 1 over K. If you multiply everything through by a coefficient, you raise the K to the power of that coefficient. Last thing is, if you look at a net reaction and you're trying to figure out the overall K, Instead of adding them like we did with delta H, it's the product of all of the equilibrium constants. So if we have a multi-step reaction and we know the K value for the individual steps, if we want the K for the overall, then we take the product of those equilibrium constants.